So things of interest to you, direct interest to you. The essays. So I believe that I got marks back to anybody who got the essay in on time or 1 day late. I believe I have your essays back. I was hoping to get them all back by today. However, this weekend something odd happened. Just before the weekend, I was kicked off of Quarkus. I was no longer able to access Quarkus or any journal articles, and also my Microsoft Office subscription said it was expired. So the university had decided that it had never met me before, we weren't friends, and we weren't on speaking terms anymore, which was odd and disturbing. It turns out I was left off of a list that I was supposed to be on. I don't know how it happened. I seem to be back now. The net result, however, was that I had no access to Quarkus over the weekend. Do you mind keeping it down a little? Yeah. Okay, so I'm a little bit behind where I thought I would be. Everybody who got their essay on time should have marks, and you should also have access to a whole bunch of comments. So if you're like, I see a mark, but how do I know where it came from? On Quarkus, there should be a comment from me with a file attached. So download that file, and there should be a whole bunch of, inside that file, a whole bunch of comments on the right-hand side in Microsoft Word, where I tell you what I think was working, what I think wasn't working, that kind of stuff. So if you don't see extensive comments on your paper, then like there should be some there. Yeah? Okay. Anybody able to see their comments? Yeah? You couldn't see the comments. Okay. I made comments on everybody. Everybody who's got a mark has got a bunch of comments. If you are absolutely unable to figure this out, you can email me and I will just send you the file with comments on it. So that's a last resort. But there should be on Quarkus a point where there's a comment with a file attached, and that's where you get your comments from. So this is suboptimal as a way of getting your comments back. But once we figured it out, once we've all figured it out, it's reasonably sort of fluid. Okay. Questions about that stuff? So if you got an extension or handed in your essay late, I will be doing my very best to get them back to you as soon as possible. Hopefully you see some justice in me getting an extension because you got an extension. Anyway, so also you don't want me marking too many in a row because I just get crusty, I just get mean, and that's a result that nobody wants. I don't want to be mean, you don't want me to be mean. So that's why I take it sort of slowly. Okay, good with that? Also, test 2 is coming up. 1 week from today, in fact. So that's a thing to think about. It's Tuesday, July 23rd, regular class time. That is, we'll start at 1:10. It'll go for 2 hours. This time it's at the exam center, room EX300. It's a very nice room. It's the kind of room that you want to write in, specifically designed for writing tests in. The format will be as follows. There'll be 4 short answer questions. So there'll be a list of 10 possible short answer questions. You'll pick 4 of them. Exact same format as last time. It's just here's a term, major term from the course that we talked a lot about. Tell me about it. Tell me its relevance. Tell me what debate it's embedded in. Tell me some things about it. So connect it up to other parts of the course. There'll be 10 points for each of those, and then 1 essay question. You'll pick 1 essay question out of 3. And I'll tell you now, basically, the topic of all 3 essay questions is going to be something like, so since test 1, what we've been doing is AI, and I've taught you basically 3 different paradigms in AI. Today is the 3rd one. We'll talk about dynamical systems today. So it's going to be something about the 3 major paradigms, compare and contrast 1 or 2 of them, argue for 1 of them over the other, that kind of thing. So it's going to be like very much like the broad structure of all of the material from test 1 until today. Tomorrow we're going to start into philosophy of mind. Tomorrow's lecture is not on the test. So test 2 is just the AI chunk. So right after test 1 till the end of today. Yeah? Yeah.
Is that type of essay similar to
Yes, in the following sense. So it's similar to the essays that you wrote. It's dissimilar in very important ways, like you've got maybe an hour to write it, and it's going to be much shorter and much less organized. But it is similar in the way that I would like for you to have a thesis that you provide an argument for. So all of the parts of your essay are supposed to be aimed at giving evidence or arguments for some view which you are defending. So that's the basic similarity. I discourage you from doing a 5-paragraph structure before. Like I know in high school it's standard to teach people to do intro paragraph, 1, 2, 3 body paragraphs, conclusion paragraph. In an academic essay that you're writing, like the short essay and the longer essay, that doesn't really work because those paragraphs end up being like incredibly long. In this one, that might work. That might be fine. So intro paragraph, you're going to tell me what you're going to argue and give me a broad overview of your argument. A couple of paragraphs in between, conclusion where you reflect on what you've said. So that's the basic structure. The basic structure is the same. You don't need to do an abstract on the essay question. You don't need to give careful citations. So I'm not expecting you to remember author dates. I'm not expecting you to do a bibliography. If you can just give me the name of ideas, that's plenty. The name of ideas, or just roughly describe the ideas, that's good too. So this is not a memorization task. This is a synthesis task where you're trying to show me that you can put all of the bits and pieces of what we've been doing together into some kind of unified whole. Yeah? Okay, other questions? About the test or the essays? Yeah?
For the essay question, can we only use information from the course, or can we use some other research?
Ah, good. So can you only use information from the course? I would be happy to see information from outside of the course. What that gives me evidence of is that you're integrating stuff from the course with other information that you've got, which is, again, a really good thing to do. This is the kind of interdisciplinary project that we're trying to engage in, where you like bring a whole bunch of stuff from very disparate parts of your life together. So that works, yeah. So if you got something from another course that you think is relevant, or like your broader intellectual life, sorry, I didn't mean to assume that school is the only place you learn stuff. Yeah, so anything from anywhere is potentially relevant, yeah, yeah. Which, as we've seen, is the main problem with cognition. Okay, other questions? Yeah?
This test is going to be covering this AI chapters that we've been studying,
Yeah.
as well as higher tests or
No, so it's not cumulative. So it's only from the after test 1 until today. So it's just the AI section. Sounds like somebody's falling down a flight of stairs. Okay. Okay. So yeah, it's non-cumulative. The stuff before test 1 is potentially relevant in the sense that there's connections between the stuff in the AI section and that, but it's not specifically going to be tested on. Yeah, I guess it's too loud. We gotta. Thank you. Okay. Anything else? Okay, so if you want to talk to me about your essay, you can do it via email, you can do it via office hours. So I'll just remind you, my office hours are just after class. You just tell me at some point you want to talk to me after class about it. I'm happy to go through it, go through the comments, talk about anything that you're wondering about. Yeah? Okay, good. It's especially a good exercise as you're thinking about writing your final essay. So things that I said on your first essay might be relevant to how you're thinking about approaching your final essay, which is a thing that's worth thinking about as you go forward. So your final essay, I'll remind you, the topic is, I'm not gonna give you questions. You're gonna self-generate the topic of your final essay. So starting to think about that now wouldn't be a terrible idea. And it's very open, it's very open. You might wanna talk to me about it, but yeah, it's very wide open. Yeah?
would be allowed to build on our lessons.
Yes, good question. So if you wrote something in your last essay where you're like, I just didn't have time to space to like say everything I wanted to say, or like hit on some body of research that I wanted to dig more into, you're absolutely allowed to take what you were working on in your first essay and develop it further in your final essay. What I warn you about is self-plagiarism, which we talked about at the beginning. So you're not allowed to just copy and paste big chunks of your first essay and copy from your first essay and paste them into your second essay. You can, however, cite your first essay. You could say, in me 2019, I argued blank. And that's a way of just sort of like using what you've already done and importing it into your next essay. You can quote yourself, you can, or rewrite what you're talking about. So avoid self-plagiarism, but other than that, you are absolutely allowed to develop what you did in the first essay further in the second essay. Yeah, yeah. And if you got interested in something in the first essay, that's a good idea. It's not a bad idea because it means you're not starting from scratch. You're not kind of like struggling to find a topic. Yeah, yeah.
So apart from the essays that you've graded, can you give an estimate as to what the average is?
I don't want to do that just yet because I'm still in the process of grading. It's in the 70s somewhere, I would say.
What is the normal, like what's the norm for this course?
I've only ever taught this course once, so I don't know what the normal average is.
Then,
For the first essay, I don't remember off the top of my head, I'm sorry. It's been a lot of courses since then. I think it's in the 70s. The standard distribution of marks that arts and science, I can tell you what the standard distribution for arts and science wants is, which is that the average should be somewhere at around 70, maybe a little lower. So the average should be below 70. And then there should be no more than 10% people getting A's or A pluses, and there should be no more than 5% failing. So far nobody has failed, and I might be above the recommended number of A's. Yeah, and I think the average is probably, the average for the first test was higher than it's supposed to be, according to, so I should, like, if I was following the arts and science guidelines very strictly, I should be just marking you all lower. Yeah, okay, yeah. I know, don't stress too much about that, Corey. You're good, yeah. Yeah, so, yeah.
about the test essay,
Yeah.
around how long should that essay question?
Hard to say. Like a few pages double spaced is probably good. It's hard to say because people's handwritings vary dramatically in how much you fit on a line.
If it were a typed up page, around how
I'm not sure. So several hundred words, between 500 and 800 words or something like that. I'm sorry, those are really rough estimates. Yeah, yeah. In my experience, the length doesn't correlate well with the mark people get on it, because some people communicate a lot of information that's well organized in a small space, and some people say every fact that they remember in no particular order, and that's not really an essay, right? Like it's not just how much can I jam onto the page, it's did you understand well enough to digest and integrate it into a coherent whole? So I would recommend don't fixate too much on length, fixate more on thinking hard about the broad structure. And the broad structure of this section has been, we did GoFi, we did connectionism, today we'll be doing dynamical systems, and each of those had some strengths and some weaknesses. Each of those had issues that it dealt with well and dealt with poorly. Those are the kinds of things that I would be thinking about if I was in your position. Yeah? Okay. Good. Other questions? Okay. Then let's do some quick review, yeah? So last time we finished off the connectionist network stuff. I won't get too deep into reviewing this material. I just want to point out some high-level features of this stuff that's going to be relevant going into dynamical systems theory. So we saw things like the wake-sleep algorithm. We saw things like the cascade correlation model. And one of the most striking features of these models, to my mind, was how much they were, to use a term that we're going to talk about a lot today, self-organizing. So one of the deep problems with the GoFi approach seemed to be that we were trying to tell the computer what the rules were ahead of time. We were trying to hand code rationality into computers. And what we found was that was really, really hard. One, because the rules that specify rationality seem to be torturously complex. But two, because one of the things that seemed to make us really rational is that we're not fixated on any particular set of rules. So what makes us rational, and this was the conclusion of the problem-solving section way back in psychology, what makes us rational is the ability to identify what the important rules are. What's the right set of rules to be thinking in terms of right now? So, I mean, if you can somehow codify that into a set of rules, that would be great, but it seemed really hard to do that. Nobody succeeded. And the attempts that were made seemed really clunky, at least in comparison to the connectionist projects in which we didn't try to code, hand code, hard code into the computer what's rational. What we did instead was build a system that looks like it's capable of learning. It's flexible, it's plastic in the sense of it can be changed. That's what we sort of hard coded into these things. And they were much, much better at doing the kind of tasks that we assigned them to, like categorization tasks. So hard coding categories seems like a pretty hopeless endeavor. The computer, A, there's philosophical problems, but beyond that, B, it really didn't work well when we tried to build machines that worked that way. But if you build a machine that's a learning machine, fundamentally that can reshape itself, that does way, way better at doing things like categorization when the data is messy. Yeah? So the self-structuring, the self-making properties of these systems seems to be what makes them radically better at doing things like categorization, things like problem solving, than the hard-coded programs that we're dealing with back in GoFi. So maybe it's the case that what we should be really focusing in is not, I mean, yeah, these things look a little bit like brains, but I think that analogy is a bit strained. We don't need to take it very seriously because they don't look all that much like brains. That's not what got us ahead. It wasn't making brain-like structures. It was making self-organized structures, structures that are capable of changing themselves in an adaptive fashion. And that's something that we can maybe see more generally across natural systems and think about where do we see this property in nature, this adaptive self-organizing structure. And maybe thinking in those terms is going to be the way we understand human cognition. So instead of thinking about fixed structures, we should think about the kind of systems that are adaptively self-organizing. Now, we also talked last time a little bit about, I won't go over this all again, but some of the problems that you get from connectionist models, it seems kind of hard, I say kind of hard, it seems like a trick to get our minds to do the thing, to get a connectionist network to do the kind of things that our minds so clearly do, which is stuff like systematicity, compositionality, that kind of thing. So this will remain a question for us as we go into third generation COG-sci. How is it that how is it that we're able to act in a sort of computer-like way? We can embody some of the functions that a computer does, like following rules in a strict, apparently non-probabilistic way, despite being these kind of like plastic, adaptive, self-organizing systems. So this will remain a question to sort of keep in the back of your mind. Okay. Good? Good. Okay, so today we're shifting to what's sometimes called third generation cognitive science. Another name under which it's found, and this is the name that's in the Walmsley text, is dynamical systems. So dynamical systems theory. Analyzing, the pitch here is we're going to analyze cognition as a dynamical system. So what is that? I have some gripes with the terminology here. People use these words in a kind of funny way. So dynamical systems theory for some people has a rich theoretical structure, but a dynamical system is literally just any system that changes over time. And that's all systems as far as I can tell. Everything changes over time. So just calling it dynamical doesn't really tell you that much in a literal sense, but people usually have in mind a certain style of analysis, a certain way of approaching the system that we'll talk about presently. So dynamical systems, it usually implies a kind of, okay, hang on. So we'll talk about that. So, and the style of analysis that I think is most commonly associated with dynamical systems theory kind of changes the way that we should understand the term analysis. So remember way back in the beginning I said to you, there's this naturalistic imperative. We want to analyze, formalize, and mechanize. Well, and what I told you about analysis was that it's the following activity: taking a whole apart into its parts and understanding the parts. Dynamical systems theory, in the rich sense of that term, is actually a kind of challenge to that traditional notion of analysis. So they've got a novel notion of analysis which is in some sense changing the way we have to think about science itself. Which is to say that they don't necessarily want to take the system apart into its parts and understand the parts. Dynamical systems theory analysis treats systems in terms of their overall dynamics. Now, that sounds kind of squishy probably, right? It sounds not that precise, but over the sort of late 20th century, what changed was a whole bunch of mathematical models were developed that allowed us to speak precisely about this overall dynamics. That phrase overall dynamics doesn't really tell you much, but there's a whole bunch of math now that lets you speak quantitatively and precisely about systems as organized wholes. So that's analysis, at least in some sense, right? It's analysis in the sense that you're trying to find categories of things. You're trying to find kinds of things that can be instantiated in a bunch of different places in the world. And in some sense, you are isolating these systems from the world. So analysis in the sense of understanding just one aspect of the system rather than every aspect of the system. We're not being historians here. We're not trying to understand things in their rich contextual nature. We're still doing analysis in the sense of just trying to understand one aspect of the system. But the connection between analysis and breaking things down into their parts is broken in dynamical systems theory. And that's the hope is that, the promise of dynamical systems more broadly is that we've got a new sense of analysis that lets us avoid some of the problems that we found in the old sense. So we had this interconnection problem. We had this problem where every time we tried to understand one cognitive process, we found every other cognitive process all mixed up in it. And that seemed to be a really fundamental issue with trying to isolate the parts of cognition. Well, maybe you don't need to isolate the parts. Maybe you can understand the dynamics of the system as a whole. That's the thought. Okay. Okay, so just a couple of basic notions from dynamical systems theory. We've got what's called a state space. So take a system that can be characterized by some number of variables. So you've got the position of a particle. The position of a particle is given by 1, 2, 3 spatial dimensions. Suppose you got 2 particles in your system. That means you need 6 dimensions. Suppose you've got 100. That means you need 600 dimensions. So given a system of 600 or of 100 particles that you want to understand in just their position and momentum, you need a time dimension and then 300 dimensions to characterize all of their locations. So if you've got a 300 dimensional space, I recommend you don't try to imagine it, or your mind will shatter into 1,000 pieces. But a 301 dimensional space can characterize exactly the state of the system, and you can, by just pointing to any single point in that space, is a characterization of the state of the system as a whole, right? So every point characterizes some complete state that the system could be in. So again, notice again, so immediately we already have this shift from parts to wholes. A single point in this system is the state of the whole system. So a single point in a state space is a characterization of the system as a whole. And what they do is, so we've got a state space, we've got some number of dimensions to characterize all the possible states of that system. Given that state of possible states, we can then, typically what we've got is a set of differential equations that describe how things change over time, and those characterize a pathway through that space, or a set of pathways through that space. So these differential equations give you some shape in the space. Yeah?
I would just have to argue, like, I understand that at first you said that the whole dynamic approach was looking at seeing things from wholes rather than parts.
Yep.
But throughout the whole reading, I was taking it as there's a bunch of parts that make up a whole, but it's important to remember all of the parts before fully go to your full belief into the whole of it, which is why it's like coming up again that even for like state spaces, you had to explain that there's parts, that it's being broken up into parts.
Sure.
Understanding the parts that make up the parts and then pushing it back together as a whole. Because like they even talk about, coupled networks and there's a bunch of different things that we're going to cover in the class, but you have to analyze them as parts, understand how they work before you can smush it all back together and say this is the dynamic
So
through connection. This is the go by view of it.
you're exactly right that you can't, it's not the case that dynamical systems theory is like, let's just never look at the parts. Let's not think about them, let's not talk about them. That's absolutely true. But that's not the relevant level of analysis for dynamical systems. So remember last time we talked about what's the relevant level of explanation? Yeah? So the relevant level of explanation for standard analysis is, I don't understand this whole. What I'm going to do is take it apart into its parts, understand the parts, and the properties of the parts are going to explain to me why the whole is the way it is. And that's not the direction of explanation in dynamical systems theory. So it's not that the parts of the system are illuminating the whole. It's an analysis of the structured whole is going to tell us why the parts act the way they do. Now, but again, you're absolutely right that this is not a one-way street. So it's not just that the whole, understand the whole, and that tells you everything you need to know about the parts. The parts are still illuminating about the whole. Like if you want to really understand the system, you should understand the parts as well. So it's not that, you're absolutely right that we don't like forget about them entirely. It's not that they're irrelevant, but what becomes relevant is the organization of the system as a whole as a kind of constraint on it. Yeah? Good, good. And that's a good point. Yeah. Yeah.
So would that mean that as opposed to understanding like the parts, like the dynamic system would be understanding the connections of the parts?
Understand.
So understanding the connection gives us an understanding of the whole versus understanding what each individual part is, giving us
Right.
an understanding of the whole.
Right, so it's organization or structure that does the explaining more than, or at the same time as. So again, this is a really good point that it's not just, the parts don't just disappear from the explanation. The parts can tell you about the whole, but the whole, the innovation here is that the whole can also tell you about the parts. So understanding the organization, the way the parts are assembled or arranged, can actually also tell you, I'm going to make this fairly controversial claim, that the organization can also help you understand the parts, which is an exact reversal of the way that we understood analysis before. And it's not like traditional analysis disappears, but we've added this other direction of part to whole explanation, whereas standard analysis in the scientific method was whole to, or part to whole. Did I say that right? Whole to part, part to whole. Yeah, so we've added the other direction. Yeah. So what we do with the state space, once we've constructed one, is to analyze it in the sense that you can understand the structure of it. So it can have features like attractors. So an attractor in phase space is a place that the system likes to go. This is a, does anybody recognize this particular picture, this fun little butterfly? This is a Lorentz system. So it's one of the earliest sort of complex or chaotic systems that were studied by Konrad Lorenz. And it was it Konrad? Was he the duck guy? Sorry. One of the Lorenzes. And it's basically just describing convection. And one loop, so it can go around, it'll go around and around in one loop. And that's convection going one way, so the sort of like the atmosphere tumbling in one direction. And then it can get this transition between tumbling in one direction to tumbling in the other direction. So this is a thing that atmospheres can sometimes do. And hanging around in one of these loops is being caught in the orbit of an attractor, and then it can move from one attractor to the other attractor. And that's a feature of, think how high level a feature this is. Every single point that makes up this trajectory is a characterization of the system as a whole. So what we're saying is, in the space of all possible states of the system as a whole, there is structure. And to understand the behavior of the system, what we're doing is looking at the structure of its state space. Yeah? So it's a kind of abstract analysis. It's a very high level analysis, and it's an analysis that really focuses on the structure of the overall system rather than the constitution of its parts. Yeah? Yeah.
This was Edward Lorenz.
Edward Lorenz, thank you. Yeah, Conrad Lorenz is a guy who studied animal behavior, and he convinced a bunch of ducks that he was their mom, and they followed him around. That was Conrad Lorenz. Edward Lorenz was an atmospheric physicist, totally different. I mean, they're both about flying in through the sky. Doesn't matter. Thank you, by the way. Thank you. Okay, so that's the kind of methodological thought here, that what we're doing is actually something radically different. The kind of analysis that we're doing, what we mean by analysis when we shift into this style of doing science, it's not just in cognitive science, by the way. This dynamical systems stuff is all over in physics. It's everywhere. So the idea is that there's a whole bunch of interesting mathematical models that are going around, kind of being passed around the scientific community, and that maybe cognitive science can latch onto these things and take this style of doing science and use it to understand the mind. That's the hope. Okay, so the kind of original apostle of this stuff, the guy who kind of made this way of thinking popular, Timothy Van Gelder. And Timothy Van Gelder argues in 1998, so we're kind of, 98, the connectionist stuff it's hot. There's still nonetheless a debate between the connectionists and the GoFi people. And Tim Van Gelder comes on the scene and says, both of you are wrong. Both of you are wrong. I got a third thing. It's better than your thing. And we should all be doing what's called dynamical cognitive science. This, by the way, so this citation, if you're curious about this, I very rarely get to see this in the literature, but there's a whole journal, not just article, but the whole issue of the journal. It's Tim Van Gelder putting out here's like dynamical systems theory, and then the whole rest of the issue is people arguing with him. So it's like 10 different people being like, Van Gelder, you're right about this, but you're wrong about that. It's like it's an academic pile-on. It's really fun, actually. So if you're curious about what people thought about this in 1998, look up this issue of Behavioral and Brain Sciences. It's fun. Okay, so in this article, which like a bunch of people in print disagreed with right away, Van Gelder argues for two basic theses. So he says cognitive systems are dynamical systems. This is the nature hypothesis. What's the nature of cognitive systems? And then second, cognitive systems are best modeled as dynamical systems. So this is the epistemic, what did he call it? The kind of epistemic thesis. Now notice that those are very different theses. The first one's kind of a giveaway. I think everybody should in some sense agree with the first one, because dynamical system really just means system that changes over time in a continuous fashion. And you're all made of atoms, right? Atoms are things that change position and velocity in a continuous fashion. So we are dynamical systems. Now, of course, you can also make parallel arguments, like we are made out of quarks. Does that mean that the best way of understanding the mind is thinking of us in terms of our quarks? Like, probably not, right? Nobody's advancing that hypothesis anyway. So just because we are dynamical systems doesn't mean that that's the right way to understand us. He also defends the much more controversial thesis that this is the best way to understand us. So forget about your GoFi models, forget about your connectionist networks. What we need are dynamical systems models. And I put up the flywheel again. I think I explained this already. I'll leave it, but this is his example of a dynamical system, his best example of a dynamical system, which you can characterize using the equations of physics, right? You can use differential equations to say very clearly what's going on in this system, but nonetheless, there's nothing even resembling a representation happening in the system, right? The system, the Watt governor keeps the train going at a consistent speed without ever thinking to itself, we're going 45 kilometers an hour, we should be going 50, I need to speed up a little. Like that thought doesn't appear, I hope you all agree, anywhere in this thing's non-head. It doesn't have a head. It doesn't represent anything to itself. It just behaves in a way that looks adaptive and intelligent. And the proposal is that that's how we should understand this system, and that's how we should understand ourselves as well. And he thinks that, so for Van Gelder's version of this is essentially that sets of differential equations are the right kind of model. That's the hypothesis anyway. He doesn't take this to be like obviously clearly established, but he does take it to be a worthwhile hypothesis. The kind of model you want to build of the mind are sets of differential equations. Yeah? Okay. So fairly controversial thesis, frankly. I'll just reiterate this because I think it's important. It's important to keep these terms crisp in your head. Too many people don't. Just saying the system is dynamical just means that it changes over time. But of course, a computer also changes over time, even at the level of being a computer, right? Not just at the level of its quarks, but if you're analyzing it the way a software engineer or a hardware engineer analyzes a computer, it's still a system that changes over time. So just saying dynamical isn't enough. What they usually mean, so I just went on about, oh, this is a whole different way of doing science. Why would that be? Just talking about the dynamical aspect isn't enough. We need to add quite a few layers to this that are usually implied by the word dynamical. So let's do that now, yeah? So what they usually mean is something like the following. They mean a complex dynamical system in the sense of, so here's two quite popular books. Chaos theory, do you remember chaos theory? Has anybody heard this term? You also had Jurassic Park, right? The old one, the first one, no? Okay, so chaos theory was a term that was big in the 80s. People were very excited about the science of chaos. People don't really talk about chaos theory that much anymore. It's not really a thing that we get excited about. But it was supposed to be, if you believe James Gleick, it's a fabulous book, by the way. You should totally read this book. It was supposed to be a science of complex systems in general. So it was supposed to be a science, a set of mathematical tools that you could use to model kind of any complex system. Where complex means it's got a whole bunch of parts interacting in a certain way that we'll talk about in just one sec. So the exciting thing was supposed to be that you could use it to model things like the weather, but also solar systems, and also economies, and also psychology, right? So it was supposed to be one unified set of mathematical tools that you could kind of use all over the place and understand systems as organized wholes. The great dream was that there would be a science of systems, a science of complex systems that characterized them all. I am dubious that there is such a thing, or if there is such a thing that it's quite as unified as it's often purported to be. So there are indeed a whole bunch of fascinating, so the more modern version of this, if you're looking for modern ways of speaking about this, complexity theory. So complexity theory describes complex systems and their complex interactions. There are indeed a whole bunch of really interesting mathematical tools and methods that you can use to model complex systems. So that's absolutely true. The question is whether they kind of hang together as a science or whether there's actually a zoo of different methods and models. I tend towards more the zoo theory of complex systems science, where it's a bunch of different tools, all of which have valid areas of application, but it's not like there's one set of tools that you can bring to bear on literally any complex system. Anyway, couple of things that they find most important about these. So a couple of things characterize complex systems in general, though. Here's the most general stuff about these things. They've got what's called nonlinearity. So nonlinearity simply means the following. It's a system in which small changes in one variable, so going from 0 to 20 on this axis, can result in large changes to the other variable, going from 0 to 240 on the vertical axis. Yeah? So nonlinearity is just that you can have a small push make a big difference. Nonlinearity was a really threatening property for a scientific theory to have for most of the history of science, because nonlinear equations resist exact solutions. It's incredibly hard to come up with exact solutions to nonlinear equations. So if you found a nonlinear equation in your theory about the world, you're like, oops, that's terrible because I can't use that. That was until the advent of computers, when we became able to deal with sets of nonlinear equations in a kind of what they call a numerical fashion. So you don't have to solve them exactly. You can do a rough approximation and then a closer approximation and a closer, so you sort of narrow down on the answer as closely as you want. That's a kind of numerical solution to nonlinear equations. So suddenly we became able to work with these things. Nonlinear equations were okay now because we had the computers which let us deal with them. So the world of the nonlinear was kind of off limits for most of the history of quantitative science. And then as computers became able to do very complex simulations and stuff like that, suddenly nonlinearity was no longer threatening. It was something we could work with. Like nonlinear phenomena are very ordinary. Like notice, so for example, boiling water. The temperature of water is one variable. From 0 to like 95, it's getting hotter. It's going linearly. It's behaving in a very predictable linear fashion. Turn the heat up on the stove a little bit. It gets a little bit hotter, a little bit hotter, a little bit hotter. After 95 or so, it starts acting in a totally different way, doesn't it? It starts to boil. So there's a radically different response to a small change in the variable. From 90 Celsius to 100 Celsius, you get this quite radical shift in its behavior, a phase transition. And unless you're nonlinear, you don't get to have phase transitions. If water behaved linearly, when you turned up the heat, it would just sort of expand slowly until it was a gas, right? Rather than having a phase transition where it boils. Okay, so nonlinearity, good. So when we're talking about, so I'm just trying to unpack the term dynamical systems, which almost inevitably means complex, that it's got a lot of parts, that it's nonlinear, and furthermore, that it involves feedback loops. So feedback loops are just when, and this is again a thing that people really didn't like in their theories if they could avoid it until about the late 20th century when computers became awesome. If A causally influences B, and at the same time, B causally influences A, that's a feedback loop. Pretty straightforward. So feedback loops typically characterize the kind of systems that people are interested in dynamical systems theory. So complex feedback loops where the A influences B, B influences A, that's one of these things, right? The flywheel is a perfect feedback loop where the higher the balls go, the slower the train goes, which makes the balls go down, which makes them go up, which makes them go down. It's a self-regulating feedback loop. Okay, so that's usually packed into this as well. So what we typically think, when somebody says dynamical systems theory, what they almost always mean is not just anything that changes over time. What they mean is something that is complex, that has a lot of parts, it's nonlinear, we've got this nonlinear response to changes to variables, and it involves feedback loops. And when you get those three properties all together, sometimes you get a system that has got the property of being self-organizing. That's for my money, that's the really interesting category of dynamical systems. So you can have dynamical systems that are not self-organizing. A bomb going off is in some sense a nonlinear. You put a very small spark to it and it makes a very big boom. It's got feedback loops, right? So the spark causes a little bit of combustion, which causes more combustion, which causes more combustion. But the feedback loop is not a self-stabilizing one in a bomb, is it? It's just blowing up. And it's in no sense increasing the internal organization of the system, right? So a self-organizing system, I think we've talked about this already, is a system that generates order inside of itself. It's a system that organizes itself. It's right in the name. It's a system that organizes itself, unlike a bomb, which is complex. It's got a lot of parts. It's nonlinear. It's got feedback loops, but it's not self-organized. So self-organizing dynamical systems are a special class of dynamical systems, and they're very interesting. They've got a lot of interesting properties. They've got a lot of interesting properties, especially for cognitive scientists. I think that you can reasonably say the connectionist networks that are most interesting are self-organizing because they've got a lot of parts. Those parts have nonlinear interactions. They have a lot of feedback loops, like in the wake-sleep cycle, like in the sort of the oppositional networks that we looked at last time. And furthermore, they don't just do a thing. They do an organized thing, right? They generate order inside of themselves. So we saw an example of this already. When I did a brief sort of teaser of this stuff. I won't show you the video again, but this was an example of self-organization. Remember this, the metronomes, and you set them all going at different angles. They've all got roughly the same, what's the word? Oh, I'm utterly losing it. Tempo, yes, thank you. Yes, in music it's tempo. So they're all going at roughly the same tempo, the same speed, but you don't have to set them off at the same angle, and they will slowly but surely come spontaneously into synchronization. Yeah? So this is a nice example of self-organization. Yeah. Let me just finish this off and then we'll take a break. So a really nice book about this, Stephen Strogatz's Sync, The Emergent Science of Spontaneous Order. Almost always the kind of books that you read about this stuff are either a scientist who cannot write his or her way out of a paper bag. They know the science very, very well, but they are unable to communicate it to you, or a science popularizer who mostly knows the science. They're good at writing, but they're not that precise about it. They make a lot of, they say things that aren't completely accurate. Stephen Strogatz is an excellent writer, and he's the scientist who does this stuff. So he's one of the scientists who's actually engaged in understanding spontaneous synchrony. So strong recommend this book. And it's a book about what's called coupled oscillators. Coupled oscillators are like this. These things are oscillators. They go back and forth on a regular cycle, right? They're coupled in the sense that because these tin cans are underneath the board, they're transmitting bumps and shoves to each other. So they're coupled in the sense that the activity of one affects the activity of another. So this is a set of coupled oscillators. And coupled oscillators spontaneously synchronize under fairly broad range of conditions. All you need is for them to have roughly the same period. That's the word I was looking for. Period. The length of time it takes it to go through one complete cycle, also known as tempo in music. So this is a really nice example of self-organization, where the system generates spontaneously within itself orderliness without anything imposing that orderliness from without. Right? There's nobody has to go around and make sure the metronomes click together. And this seems to be the case for things like heart cells. Your heart cells beat in synchrony, and you want them to do that. When they fail to do that, that's a heart attack, right? Or a heart palpitation. Scary thing to happen. Metronomes, neurons, we'll talk about neurons. They do both synchrony and asynchrony. You can see fireflies. So male fireflies, one of the reasons that they flash is to attract female fireflies, sort of to advertise their amorousness. And one of the ways that some species of fireflies enhance this signal is by going into synchrony. So they're watching their nearby firefly pals, and kind of matching up with them. And you can get whole banks, whole river banks. I've seen video of whole river banks of fireflies all flashing on and off at the same time. It's quite remarkable. So the thought here is, and this is just one example of a type of self-organizing system. We'll go through a few other types today. One example of a type of self-organizing system for which we have really good mathematical models. And the interesting thing is, it's the same model for heart cells, neurons, metronomes, and fireflies. All you have to know about the system is that it's a set of coupled oscillators, and then you can mathematically model the ways in which it will go to spontaneous synchrony. So again, going back to the part wholes thing, think about this. So I want to understand why heart cells fire in synchrony. That's an important property of heart cells. Now, there's two strategies that you could use. One of them is to look very carefully at the properties, the specific properties of heart cells. That is to take the system apart into its parts and understand its parts. Now, I don't want to say that that's not a valid strategy. There's probably things specific to hearts that you want to know. But here's a whole different strategy. It's a strategy where we're understanding the system in terms of its overall organization. And that's a strategy that allows us to see not just what's going on in heart cells, but what's common between a whole bunch of apparently very different systems. So we're understanding the system as self-organizing, and we're trying to see what we get is a mathematical model that tells us how it's similar to apparently radically different systems. That is to say, spontaneous self-organization, spontaneous synchrony is multiply realizable. Right? So that's a nice property for cognitive scientists to have multiply realizable properties. And it's a shift, it's a deep shift in the way science tries to understand and appropriate features of the world, right? Instead of doing this breaking down into parts thing, they're saying, no, let's stay at the level of organization. If you stay at the structural level, you can learn different things. Not that you learn nothing from the parts, but you can learn a whole different set of things by looking at their organization as a whole. Okay, let's take a break. Come back at 2:15. We'll talk about a few other types of self-organizing systems. Okay, so we were talking about spontaneous synchrony. That's one kind of self-organization. Let me show you another kind of self-organization, which I think is a different kind. So this is the emergence of convection. Yeah. Let's see. So this is what's called Rayleigh-Bernard convection. Is it playing? Yes. Okay, so imagine you got any fluid heated from below. That red stuff is heat that's happening. So mostly what it's going to do is the heat is just going to move through the system smoothly, right? So heat is sort of rising up, but then once the fluid that's warm expands, so you warm a fluid, it expands, which means it rises up. And then it gets up high away from the heat, and that makes it cool down. And then it wants to go back down again. So what happens spontaneously is that these rolls emerge. They're called Rayleigh-Bernard convection rolls. So convection is just when anytime you've got a sort of fluid heated from below, it tends towards making these spirals, these convection rolls. Yeah? Now, from the perspective of any given particle in this system, going round and round in a circle is a very improbable thing for it to do. It's very unlikely that any given, so of the space of possible ways that any given molecule of the fluid could move, going round and round in a circle occupies like 0% of that space, to a very good approximation, 0% of that space. So it's a wildly unlikely thing for a single individual particle to do, but here's a simulation of them doing that. And this convection happens all the time. It's like an extremely common way for fluids to move. It happens all the time. So it's not an unlikely event as an organized whole. So what that tells us is that the probabilities to understand why the particles are moving the way they are it's not enough to cite the intrinsic properties of the particles, because just looking at the intrinsic property of the particle, this is extremely unlikely, right? An explanation is supposed to make the thing that you're explaining sound reasonable and likely. What explains the movement of this fluid is not the properties of the particle, it's the organization of the system as a whole. Yeah? There you are, Rayleigh-Bernard convection. It's one of my favorite kinds of self-organized systems. It's what's called a dissipative system, because of course, we're all familiar with the second law of thermodynamics, right? Which says that you never get energy for free, right? Systems always generate more disorder than order, right? Oh, we don't want to learn about that. That's a different class. So this is from when I was trying to learn Excel. Okay. Okay, so this person, Ilya Prigogine, got a Nobel Prize for his work on what are called dissipative systems. A dissipative system is this. Why is it called a dissipative system? It's because a system that's generated order within itself is actually better at dissipating free energy, which is to say it's actually better at creating disorder in the rest of the universe than a system that doesn't generate self-order. So in a non-convective regime, before it starts doing this rolling thing, the system will actually like retain more heat than in a convective regime. So the convective regime is better at getting rid of its heat, dissipating its heat, than the non-convective regime. So by producing order inside of itself, it's actually more efficient at exporting disorder to the rest of the universe. And that's basically what every living thing is, right? Every living thing is a highly, highly organized system, very low entropy, very low disorder. But we do that by messing up the rest of the universe, right? Every time you clean your apartment, you're generating more, by making a little bastion of order for yourself, you're generating more disorder in the rest of the world. So never clean your apartment? Or get used to the idea that, you know, disorder is something that we're just going to do. Those are your options as far as I can tell. So a different set of math to characterize dissipative systems than to characterize spontaneous synchrony. It's a different set of mathematical tools, but nonetheless, it's a set of mathematical tools that applies widely. It applies to a whole bunch of different systems. So for example, you get convection in the sun, in stars in general. You get convection in you get convection in the magma under the ground. You get convection in a pot of oil if you heat it properly. You get convection in the atmosphere. So you get convection all over the place in all kinds of different media. It's very easy to get convection going. The same math characterizes it across those different scenarios. That is to say, convection is multiply realizable. So that's another interesting example of like what we were trying to get out of GoFi. Remember that was like, yo, GoFi must be true because it's the only way we can think of to get multiple realizability. Well, here you go. Here's another way. That is to say, self-organization is a way of getting multiple realizability. Okay, so that was two examples of different types of self-organization. We'll do at least one more before we're done. But I want to shift to somebody who's the argument of somebody, unless we have questions. No? Yeah? Yeah.
I mean, doesn't that kind of self-organization, though, kind of pale in comparison to the self-organization that we're actually worried about?
So, yeah. Yeah, so this is fairly unimpressive, right? Going round and round in a circle. If I built you a robot that goes round and around in a circle, you wouldn't be like, it's intelligence, right? You shouldn't. So absolutely, that's right. Absolutely, this is a very simple example. Partly chosen for pedagogical reasons, so I can start slow and kind of ramp you up. Partly to get what I'm doing today is trying to show you the style of explanation that third generation COG250 proposes. So I'm trying to make the argument that this is a really deep shift in the way of modeling these systems and the way of understanding these systems. That is to say, we're doing science differently now. And it's not something that happened within COG necessarily. Right now we're doing the kind of history of this way of doing analysis through physics. And dynamical systems theory proposes basically to grab a bunch of tools from physics and apply them to the mind. So that's within cognitive science, the dynamical approach is to say, hey, physics, you've been doing a bunch of cool stuff that we think we can use to understand the mind. We'll import your mathematical tools, your conceptual tools, your explanatory style into cognitive science and maybe make some headway. Yeah. I'll do one example that I think actually starts to deal with the level of complexity where we're at. But again, I mean, we're not there yet. So I can't show you like a full-blown explanation of the mind because those don't exist yet. But what we've got is potentially a way of dealing with the kind of apparently insoluble problems. So in this course, we keep hitting up against problems that look like, that's impossible. We can't possibly solve that. You might look at the frame problem and say, that is impossible. And actually, the guy who designed this course, John Verveake, when he first taught it, the conclusion of the course was, the frame problem shows us that artificial intelligence and a science of the mind is impossible. So give up. And then this kind of stuff started showing a way that maybe we don't have to give up. Maybe we've got a way forward. So this is basically the point of this is just to say, maybe possibly there's a way forward. Maybe possibly this is it. Yeah. It's a fairly modest claim, I think. Okay, so we've been doing a bunch of physicsy stuff. You're probably, once again, thinking, wasn't this supposed to be a class about cognitive science? So let's get back to that. So I'd like to talk a little bit about this book by Alicia Huerero, Dynamics in Action, which defends in a very rich sense of dynamical systems, defends a dynamical systems theory. So the theory of complex adaptive systems can help understand the mind and furthermore its relation to matter, which is a big claim. This is a timely book, so published in 1999. There was a big controversy about this book because Alicia Huerero accused another guy of plagiarizing it. And if you go through his book, almost all of the ideas in this book are in his book, and his book came after. So either two people came up with all of these ideas at the same time, or somebody ripped off Huerero. I won't name names. You can Google it if you're curious. So these are ideas that are at least sort of in the air, if not so good that somebody stole them. Okay. All right. So and Huerero makes the case that basically self-organization is going to be the framework in which we can begin to understand how the mind works. That is, these tools are going to allow us to analyze the mind in a way that allows us to formalize and maybe mechanize. She's going to make the case that even more deeply, she makes the case that I've been sort of articulating already, which is that this is going to involve using the science of self-organization to understand the mind is going to involve rethinking science in a really profound way. And it's a way that takes us practically all the way back to Aristotle. So there was a reason why I told you this little stuff about Aristotle. And part of it is to understand what Huerero's proposal is going to be. So what she says, so this part is uncontroversial. The scientific method as it's understood today, or has been understood traditionally, operates exclusively in terms of efficient causation. If you remember, Aristotle's got 4 types of causes, 4 types of explanations that he's willing to understand in the world. Efficient causation is the kind of push and pull, right? When you hit the cue ball and it scatters the other pool balls, that's you explain the scattering of the pool balls in terms of the smack of the cue, right? So that's efficient causation, pushing and pulling causation. And for Descartes, for Hobbes, that's the only kind of causation that you're allowed to cite when you're trying to understand and explain the world. what we did when the scientific revolution came around was banish the other causes. So formal causation, remember we talked about forms and formal causation, final causation, purposes, goals, none of that. The scientific revolution said, that's not allowed anymore. We're done with all of those other kind of causes. And there was a good reason for that, really good reason. So one of the things that only allowing efficient causation does for you is it eliminates circular explanations or circular, it eliminates circular causation and therefore circular explanations. We had an example already of circular explanations. Remember the homuncular fallacy? I'm going to say, how does vision work? Well, there's a tiny person in your mind, in your head, that sees what you're seeing. How does their vision work? Tinier person. And them? Tinier person. And on, right? So it's a circular explanation. How does intelligence work? Well, you've got these little parts. They're intelligent. Good, okay. Doesn't really get you anywhere, right? Doesn't really advance the project of understanding when you have a circular explanation. If you're trying to understand something, you don't want to invoke that thing to understand it. Really famous example from Molière. He was making fun of some scientists, some scientists who thought they were pretty clever, some doctors. He's in a book. He asks, "Why does opium make you sleepy?" And the answer that the clever scientist medicine guys give is, it has a dormitive virtue. Dormitive virtue. What does dormitive mean? It's a sleepy. It's got this property of sleepy making. So if I say, why does opium make you sleepy? It's got a dormitive virtue. What do you mean by that? It makes you sleepy. Okay, so as an explanation, you should think, that's a bad explanation, right? That's not a good explanation. That's exactly like the homuncular fallacy. It's a circular explanation. You're just invoking the thing you're trying to understand. So efficient causation, and you might accuse Aristotle of this. Why does the rock go down? Well, that's where it wants to be. Why does it want to be there? Well, because that's what the kind of thing it is. What kind of thing is it? It's the kind of thing that goes down. Not super satisfying as an explanation, perhaps. So we eliminate a whole bunch of bad explanations. By only focusing on efficient causation, you can eliminate a bunch of bad explanations, circular explanations, that we don't really like. So that's a pretty good reason to have only focused on efficient causation. However, there's reasons to believe, Horero wants us to think, that we can't get by with just efficient causation. And she repurposes an argument from Kant, Immanuel Kant, to show this. So, Immanuel Kant, in his Critique of Judgment, his third critique, starts thinking about living things, trying to understand the explanation for why living things are the way they are. So, what causes trees? Well, leaves. Leaves help build the tree. What causes leaves? Trees. Okay, so that's not really what I don't know if any of you have read Kant. If he was this clear, we would all be a lot better off. He's got a better argument than this. He's got a better argument than this. So here's a slightly more elaborate version of his argument. So, living things, he says, are self-organized. What does that mean? So Kant actually coins the term self-organized, and he's got a very specific thing in mind when he says it. So to be self-organized is to have the following property. All of your parts are such that they construct you as a whole, and you as a whole construct all of your parts. So all of your parts are made bespoke by you. You made them yourself. Congratulations, right? You synthesized all of the proteins, you put all the pieces together, you made your own body, right? You generated your own body. And you did it in a way that was sort of adaptive to your needs, mostly. None of us are perfect, but like mostly your muscles are about as strong as they need to be to do the tasks that you ask of them on a daily basis, right? Mostly your metabolic system is adapted to digest the kind of food that you put in it on a daily basis, right? So you are in some sense, in this reciprocal causal process where you generate your parts and your parts generate you. That's what Kant means by self-organized. You're self-making, self-generating. Okay. But that sounds a lot like this, right? Which is this. I mean, if this is a really crude way of putting it, but if this is what if what self-organization is, that's clearly a causal circle, right? It's circular causation. It's A causing B and B causing A. Okay, so living things are self-organized in the sense of being self-makers. Self-organizing requires circular causation, premise 2. Circular causation requires circular explanations, premise 3. Circular explanations are not allowed in science. We just said those are terrible. Circular explanations, those are bad. We established that, right? Therefore, there can never be a science of living things. This is Kant's conclusion. He says, it is absurd to hope that maybe another Newton may someday arise to make intelligible to us even the genesis of but a blade of grass. So there can never be a science of biology, is the conclusion of this argument. Now, there is a building in this campus that says biology on the front. We can either believe that those people are utterly deluded about what they're doing, or that Kant turns out to be wrong, that actually we do get to have a science of biology. But notice that this argument is logically valid. It's an argument that if all of the premises are true, then the conclusion follows necessarily. So we got two options. We can go march down to the biology department right now and tell them that Kant says they're out of a job. I'm up for that if you guys are. Or we can admit that there's at least one premise here that's got to be wrong. Let's go storm the biology. There are much more important places to be storming right now. If we're going to storm something, let's go to the government, or I don't know. Yeah, let's go storm Area 51. The internet's a weird place. Okay, so just to give Kant his due, he doesn't mean that you can't make claims about trees. You can count the number of trees in a given area. You can measure how much they weigh. But these are all specific things about trees. So you can learn lots of specific facts about living things, according to Kant. But what you can't do is come up with a science, the generalizations about them. And he thinks that's because living things involve circular causation, which requires circular explanations, which is not okay by the scientific method. And Kant's a really big fan of the scientific method. Yeah?
I were to, because I'd agree that it's valid.
Yeah.
I don't think it's valid.
Good.
I would probably argue that circular explanations are not allowed in science. I would say that's not true.
Ah.
I'd say that you just kind of listed off plenty of examples of circular systems that they exist.
Right.
So
I think that's to kind of nudge you onto where the rest of my PowerPoint slides are going to go. I think you're more objecting to premise 3 there, which is to say circular causation. So these circular systems exist, right? A causing B, B causing A. That seems to be a fact in the world. But maybe understanding them doesn't require circular explanation in the bad sense of circular explanation. Yeah?
Yeah, I would, I guess.
So you want to deny P4 and say, actually, we're going to rehabilitate the notion of circular explanation.
Yeah, or create,
Yeah.
basically create some exceptions.
Yeah.
In the scientific method to allow for circular explanations, as if they are something that can be vegan.
Right.
So if opiates have a state of virtue.
Yeah, a dormitive virtue. Yeah.
It is true that they do put you to sleep, right?
It's true.
So, I would say that, and in terms of understanding self-organizing systems,
Yeah.
understanding the property of a particular thing is sufficient so long as you understand how it's connected to the whole. So I can't see why there needs to be a problem with that.
Right. Okay, so watch where we go, and you might find that actually we're in agreement on this. So you might either reject P3 or P4 here, yeah? Those seem to be the most promising places to be like, nah, this argument should be, we should reject at least one of them or storm the biology department, which we've already said we haven't got time for, busy people. So that seems to be like the most promising place, yeah.
Could you object to P2?
Self-organizing requires circular causation. So not if what you mean by self-organization is what Kant meant. So the examples of self-organization, this is another axe I've got to grind here. People use the word self-organization in quite different ways. The first couple examples that I showed you, you probably could reject P2. So the thing about spontaneous synchrony, the thing about convection rules, yeah, maybe you do want to reject P2. But when Kant uses this word, what he means is the parts explaining the whole and the whole explaining the parts. Let me try to deepen this a little. So this is a really good question. So circular causation and circular explanation. What do we do when we explain something? What we do is we make it obvious why it is the way it is, right? So here's one of Kant's examples, just to bring this out a little bit more. So why do birds have hollow bones? Why do birds have hollow bones? As a matter of fact, birds have hollow bones. Why? Now, there's no parts level explanation for that, in the sense that there's no mechanical reason why they have to have hollow bones. We have solid bones, so we can like fall over and not have our bones shatter immediately, right? We want good, sturdy, solid bones. Our bones are solid. Bird bones are hollow. Why? Well, so the fact that it could have been otherwise, that is, birds could have had solid bones, right? From a mechanical point of view, from the point of view of the parts, there's nothing that excludes solid bones. The reason why they have hollow bones is because they spend their days flying around. So to be light, there's a premium on having light bones to make it easier to fly. That's why they have hollow bones. But you don't get that from understanding the parts. You don't understand that from looking closely at the bones. What you need to look at is the whole lifestyle of a bird, right? The whole way it makes its way in the world. You need to understand that it flies, that that's how it gets food, that that's how it moves around. And that's not a parts level fact, right? That's a fact about the bird's life as a whole, its ecological niche, its embeddedness in a whole way of getting through the world, yeah? So understanding hollow bones is not something that you can do by just looking at the parts. It's something you have to look at the whole. And to understand the whole, of course, you have to understand the parts. How is it that birds are able to fly and have this lifestyle of flying around that they do? Well, they've got things like wings and feathers and hollow bones. So the way to explain how the parts got the way they are is actually to cite the organization as a whole. And the cause for the parts being the way they are is to cite the organization of the whole. And the cause of the organization of a whole is also obviously the parts, right? So you need both constraining each other at the same time. So that's what Kant means by self-organization. And I understand that he's got his own weird thing of it. So with that in mind, are you still?
Well, I don't know if I find that it's really circular causation. If it's really circular causation, it's unchanging, isn't it?
It's okay for it. Interesting. Interesting. I think it's okay for it to change. I think it's okay for the parts and the wholes to continue to constrain each other through development.
But then it has to start somewhere, right?
It does, yeah. So it has to start somewhere that doesn't have the organization of the whole imposing itself or something like that. Yeah. Interesting. Yeah, just like life in general, right? So if being a living thing organizes your parts, if you go back far enough in all of our family trees, you get back to something that wasn't alive. I mean, it was some time ago, but eventually you do get back to, so you don't have that top-down constraint anymore. So that's true. But you might not want to call those abiotic precursors self-organized. So once we get into being alive, then it's got to be self-organized, and then it seems to require this. Yeah? Okay. Yeah.
If you have self-organizing things that aren't alive, like
To-
crystals, if you're going to click your crystals and self-organizing.
Totally.
So
Well,
you could call it self-organizing systems. Like the weather is kind of self-organizing, right?
okay, so this all crucially depends on. I'm sorry, I'm unable to not be pedantic about this because I wrote a bunch of stuff in my thesis about it. So it's like, it's ingrained into my very being to be picky. So in some sense, I would argue that crystals are not self-organized because they're certainly not self-organized in Kant's sense, because the properties of you can explain why it became a crystal by citing the properties of parts. Like, look, it's just the lowest, for a carbon atom, the lowest energy state it can be in is being linked together in a regular lattice. So that's a fact about individual carbon atoms. So if I want to understand why it is the way it is, I can cite the parts. So in that sense, a crystal is not self-organized. It's the kind of, what makes something self-organized for Kant is that it could have been, at the level of the parts, it totally could have been some other way. Like the bird's bones could have been solid rather than hollow. Our proteins, when you eat food, you take in a bunch of proteins that you rip apart into their parts and you reassemble. Your genetic code tells you how to reassemble them into proteins that you like. You could have made different proteins out of the same food. So you break it all down and then you reassemble it into the parts that you make up you, according to some very specific scheme that could have been otherwise. So it's the fact that the parts could have been otherwise, and the only real way to understand the parts is to understand the organization as a whole, which makes it, for him, self-organized. Yeah?
Okay, but
Okay.
like, I mean, I don't know the chronology on this, like Kant or Darwin came first, but like.
Oh, yeah. So Darwin shows that Kant's wrong, basically.
Okay.
Yeah. So Darwin comes well after, and that's, anybody who after Darwin would have a lot of gall to say this sort of stuff, because if Darwin meets this description exactly, he's the Newton of the blade of grass, right?
Right.
Yeah.
Then circular causation doesn't seem to require circular explanation because the Earth is appealing to evolution. Where it's like, it has hollow bones, because if it had solid bones, it wouldn't be able to fly and would get.
Right. So what I'm gonna argue is that evolutionary explanations are a kind of maybe we might want to say non-vicious circular explanation, or we've got an explanation of it that's not circular in some sense. So that's exactly where it's very good. That's exactly where we're going. Okay. I bet you didn't expect to be doing Kant when you woke up this morning. Right. Okay, so Huarero's suggestion, how do we get out of Kant's problem such that we can have a science of biology? Well, it's to allow final and formal explanations back into the scientific worldview. We're not going back to Aristotle's whole physics, because that didn't work. Aristotle was wrong about a lot of the sciencey bits. But nonetheless, she argues, if we're really going to understand formal or self-organization in this rich sense that Kant means it, we need at least formal explanations and probably final explanations as well. So what I'm going to do for the rest of this lecture mostly is talk about formal explanations. We'll do a little bit about final explanations right at the end. But let's think for a while about is she saying we should go back to the theory of the forms, which we said in categorization is wrong? No, but she's got another version of formal causation that she thinks does make sense, and does make sense of both Kant's notion of self-organization and the kind of self-organization that we've been talking about throughout this class. So let's think a little bit about one of the assumptions of the scientific worldview is that everything should be understood in terms of causes. Why is anything the way it is? Well, because of the causes. Huarero thinks that we actually need to start thinking about causes as well as constraints. And formal cause is going to end up being a kind of constraint on the system. So think about convection, the convection rules I showed you. What makes the system go round and round? Well, you can give a pretty good explanation of that, right? So I hope I gave you something like an explanation earlier. So the heat, you heat it from below, it gets less dense, it moves up, displaces water, which then cools off, and then goes down, gets more heated up, and round we go. Ta-da! Have to explain the system, right? No problem. Oh, okay. So now, what makes the individual particle go round and round? Very weird, as I mentioned, it's a very weird thing for a particle to do. Ilya Prigogine says it takes up exactly 0% of the space of possibilities for the particle. Like, except in a convection roll, particles would just mostly, they do Brownonian motion, they just sort of bounce around randomly, yeah? And heat transfer happens just by like them going, just randomly jiggling faster, rather than having a very specific trajectory through the space, yeah? So what makes the particle go round and round? I propose to you that you can tell at least 2 stories about this, and that if you don't tell both, you're missing something about the universe. So here's one story that you could tell. We got an individual particle. Let's call him Tim. Tim is going round and round. You ask Tim, why'd you go round and round, Tim? Tim could tell you a complete causal story about like, well, this particle bounced me this way, and then that particle bounced me this way, and then on and on and on, right? So for Tim, there's a complete mechanical story about the trajectory through the space, right? You can tell a complete mechanical story about any given particle. This is a numerical simulation, which means that, it's a molecular simulation, which means that they're actually simulating the individual particles, and there is, somewhere in their computer, a complete list of all of the things that caused it to move the way it did. So there's a mechanical explanation for why the individual particle does what it does. But there's another explanation, isn't there? There's an explanation that relates that part, Tim, to the system as a whole. Why is Tim going round and round? Because Tim is undergoing convection with all of his friends. Is that not also an explanation? So, yeah, I would never dispute that there is a complete mechanical parts level explanation that gives you one way of understanding Tim's movement through the system. But there's also, movement is very, very weird. It's very contingent unless you understand that Tim is embedded within a system that's undergoing convection. And then you've explained it in a really robust way, right? You've explained it in a way you're like, oh, I understand not only this system, but how that relates to other instances of convection throughout the universe. That's pretty nice. Right? So, and what we've done in that second whole level explanation. Now, so the mechanical explanation is entirely in terms of causes, right? It's entirely in terms of pushes and pulls. Descartes would have loved it. Hobbes would have loved it. Pushes, efficient causation. But the whole level explanation, we're trying to understand what Tim is up to relative to the level of the whole. What we're saying is there's a kind of constraint that's been imposed on the system, right? A constraint rather than a cause. It's not something that absolutely requires Tim to move the way he did, but rather it's a set of things that make impossible a set of possibilities that used to exist, yeah? Okay, so I'm gonna use constraint in a weird technical way. Well, Guerrero is gonna use it and I'm gonna tell you about it. Let's distinguish enabling constraints from limiting constraints. So limiting constraints you're familiar with, yeah? Limiting constraints you know lots about. That's the normal way of using the word constraint. You say, do not enter. That's a constraint on your movement. They say you're not allowed to go there, right? So what are enabling constraints? So Guerrero's suggestion is that we can think about both constraints that make things impossible, limiting constraints, and constraints that make things possible. Now, my favorite example of this is that somebody imposed literacy on you, didn't they? Right? So when you were a kid, I don't know, hopefully somebody who liked and cared about you, said, you're going to learn how to read. And you say, I don't feel like learning how to read. I feel like running around like a little kid. And they said, shut up. Right? Now, that's a constraint that was put on your behavior. It's often quite heavy constraint. But did that reduce the number of possibilities in your life or expand them? I would propose to you that the possibilities for your life are greatly expanded by somebody imposing literacy as a constraint on you. Yeah? Wow, there's a party out there. All right. So that's a kind of enabling constraint. This is how I reconcile like a broadly like, I hope people get to do what they want with being a teacher where I impose a bunch of stuff on you. So my hope is that I'm imposing a bunch of enabling constraints on you. That is, I'm requiring things of you that actually make more things possible in your future life. Well, that's my hope anyway. I mean, there's no promises, but that's the goal. And notice that this isn't just about pedagogy and child rearing. This is a fact about lots of systems. So currently, you've got a bunch of potassium in you, right? Hopefully, you've got an adequate quantity of potassium. And most potassium doesn't participate in cognition, right? The potassium in your brain is helping you think. It's participating in the process of you thinking. Now, almost all the potassium in the universe is not engaged in that process. That's not a possibility open to most of the potassium in the universe, right? Right. Like most of it's sitting around in a rock somewhere. And although it's not being, so what's making the possibility of the potassium in your brain open to it participating in cognition is a very elaborate system of constraints. Your brain is a very specific and odd, relative to the space of all possible organizations of matter. Your brain is a very odd organization, very specific, and it imposes very specific constraints on what you're going to do. And that's the way you want it, right? That's the way you would like it. You want to be under heavy constraint, under heavy organizational constraint. So the fact that you are organized in this very specific way enables the possibility for your parts to do things that they otherwise couldn't do, like cognize, like live and breathe, like participate in the world, right? So those are enabling constraints. And what Horero wants us to shift our thinking in terms of is instead of seeing the world just in terms of causes, we should also see the world in terms of limiting and enabling constraints. Limiting and enabling constraints are factors of organization. Right? They're imposed by the organization of the system in which you're embedded. And that's a formal fact about the system. It's a fact about the form in the sense of its organization, its structural, functional organization. So when you explain, so according to Horero, when you explain something using formal explanation as a formal cause, what you're doing is citing the constraints, both limiting and enabling, that make it the kind of system that it is. Okay. Now, we made it to evolution. Evolution is like this. So evolution is a theory, is a dynamical systems theory in the sense of Horero. Now, she proposes, and I think is exactly right, that you can understand evolution as a series of interacting, enabling, and constricting constraints. Limiting and enabling constraints. Constraints which close down the possibilities and constraints which open up the possibilities. So a constraint that closes down the possibilities of biological form, one constraint is natural selection. So if you find yourself having the kind of form that doesn't let you survive, then you don't get to pass on your genes to the next generation. So that limits the forms, right? It's a heavily limiting, selection heavily limits the possibilities of biological organization. Yeah? It's a limiting constraint. There's also enabling constraints. For example, mutation. Mutation opens up the possibilities. Recombination of genes through sexual reproduction. It opens up the possibilities. And evolution is a theory that says here's how species change through time and how they stay adapted to their environment. The interplay of those two, and a bunch of other, by the way, a bunch of other limiting and enabling constraints. So it's the interplay of those two types of constraints shaping matter as it develops through time. That's how evolution works. And this way of thinking about evolution is in some sense invoking formal explanation. It's invoking these constraints rather than causes. Because natural selection isn't a cause in the normal sense, right? I don't know anybody who ever died from natural selection. Oh, natural selection got me. Right? It's not, you can't see it acting in the world. Natural selection doesn't act in the world on individuals. When they do the mathematical models in evolutionary biology, natural selection only appears at the population level. So you can detect natural selection when there's differential survival and reproduction, but differential means differential at the population level, not at the individual level. Nobody ever died from natural selection. Nobody ever reproduced due to natural selection. That's not how it works, right? So the individual level causes are one story you can tell about me. So how did I end up with opposable thumbs? Here's a story you could tell. Well, my parents had opposable thumbs. Their parents had them, and on, and on, and on. You don't have to mention natural selection once in that, right? It's just the fact that my ancestors all had opposable thumbs, mostly, I don't know, some variation, but like mostly had opposable thumbs is the story of how I ended up with opposable thumbs. There's another story you could tell, though, at the population level, where natural selection favored those primates that happened to have slightly more opposable thumbs than the people around them. So that's a different story you can tell, and it's a story about this constraint, this limiting constraint via natural selection, in playing against the enabling constraint of mutation and recombination. Okay, and I'll just note, sounds to me a lot like, and I think you can reasonably describe the wake-sleep algorithm in very similar terms. So remember the wake-sleep algorithm, where you feed it data and it kind of narrows down on trying to make generalizations. So give it some data, tries to build one layer of generalization, another layer of generalization, another layer, another layer. So it's narrowing down the possible generalizations available to it. And then you flip it over to the sleep cycle and it opens up the possibilities, opens up the possibilities, opens up the possibilities. And you allow these two processes to play off each other, and what you get is a reasonably good generalization machine, a machine which grabs generalizations from the environment. So I think, and it's reasonable to call this a self-organizing system in the robust sense that we've been talking about. That is to say that it's kind of generating its own parts. It's generating its own internal structure to a substantial degree. And that's what's characteristic of the really successful, it seems to me, over the last 20, 30 years, the most successful connectionist architectures are the ones that allow for the most self-organization. And the shift from the 80s version of connectionist networks to the current generation was not just having them narrow down on generalizations, but having the interplay of narrowing down and opening up, limiting and opening up constraints. We've got two senses of dynamical theory going on here, and I want to just offer this distinction to you to kind of keep these clear in your head, because people generally don't, and you'd be better off if you did. So Tim Van Gelder, his original dynamical systems theory, the one that Walmsley talks about in the textbook, mostly what he means is uses differential equations, which are these things. Yeah. Usually he means, what he means is we're going to model these using some tools from physics that look like this. what I've just been describing to you is the thesis from Alicia Guerrero, who sometimes says dynamical systems, sometimes people say complex adaptive systems, and it's a kind of different theory. It's that she's okay with using these equations. It's not like she's saying no to this, but the whole part-whole reciprocal causation thing, that's a whole different kettle of fish than just saying dynamical systems, or just saying differential equations, yeah? So we got two levels of dynamical systems theory that maybe we could be subscribing to. Good to keep them separate in your head, yeah? So there's the, yeah, okay. Now let's do a little bit of, like, how does this actually look in COG250? Because this has been very abstract. I've been talking about formal causation and Aristotle and Kant. Let's talk a little bit about what this looks like in the brain and models of how the brain relates to cognition. So recall this stuff about spontaneous synchronization. I said it happens in neurons. Neurons are indeed the kind of things, they are oscillators in the sense that they go through a cycle of firing and rest and firing and rest. So that's the sense in which they're oscillators. They fire, fire, fire. And they're coupled oscillators in the sense that one neuron firing affects whether the neurons around it fire and at what rate. Now, pardon me, so neurons that are very, very close to each other in the brain are almost always in sync, right? They're almost always synchronized. However, one of the interesting proposals that's kind of on the table right now, and is producing a lot of good empirical results, is that long distance synchronization, synchronization across like several centimeters or further, is one of the ways that different parts of the brain share information and cooperate on projects. So the making and breaking of neural synchronies is one of the ways in which your brain operates as in a coordinated fashion. So if you, there have been experiments where they measure the neural synchrony, for example, in a cat, and the cat knows that when it gets a visual cue, it's going to go press a lever and get a food reward. And when you measure, so you give it the visual cue, and as soon as that happens, in the cat's brain, the part that registers visual information and the part that plans motor activity sync up. And it ambles over and presses the thing, and then they desynchronize. So it goes from being out of sync normally, cat's just sitting there. When it's got some task where it needs to coordinate its vision with its motor activity, those two separate parts of the brain start humming together. They start firing in synchrony, and then when the task is over, they go back out of synchrony. And this seems to be a fairly general feature of brains, not just cats, humans as well, other brains, and brains attempting to do coordinated activities. And you might be thinking, boy, I wish my brain was always in sync all the time. And no, you don't want that because that's an epileptic seizure. You want your brain to be sometimes in sync and sometimes out of sync, right? You don't want it to be all firing all together. You want it to be synchronized as necessary and unsynchronized as necessary. So the really interesting thing is that your neurons seem to be poised right at the edge of being synchronized and desynchronized. So it looks like your brain is tuned very, very carefully to be where it's almost going to jump into synchrony and it's almost going to fall back out of synchrony. So you don't want it to be super hard for synchrony to happen. You don't want it to be super hard for you to like coordinate your ability to see things with your ability to move towards them, right? That seems to be, you want it to be very, very fluidly, quickly able to coordinate, but you also don't want it to be a cascade of coordination because again, that's like a seizure. That's if you just stay there, you just die, right? So you want it to be right on the edge, and it's proposed that what your brain is doing is another kind of self-organization in this sense. It's self-organized criticality. I propose that this is a different kind of self-organization than the first two that we saw, but it's nonetheless a kind of self-organization that you can identify across a bunch of different systems. It's multiply realizable. So this was done by a scientist called Verveake. He got a Nobel Prize for it. Usually if you're going to get a Nobel Prize in science, you need like $1 billion particle accelerator or a really fancy telescope. This guy worked with rice piles, little piles of rice. So here's self-organizing criticality. So you got a platform or something, you got a little flat space, and you just start dropping grains of rice. Drop, 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 a steady flow of grains of rice. Or sand or whatever. He used rice, but, and it'll slowly build up a pile, right? Slowly build up a pile. And then at some angle, it will start having little avalanches, right? Little avalanches will start. And the slope will go up and up and up and up until it reaches that angle, and then it'll drop back down and go back to that angle, and then drop back down, and go back to that angle. So that angle is called the critical angle. It's the angle where it's just at the edge of going through a phase transition. That is, from going from a stable state to an unstable state where it's undergoing an avalanche. So that critical angle, and the system seems to be tuning itself to right on the edge of a phase transition. That's self-organizing criticality. That is to say, that's a system that seems to naturally tend towards this quite important point in its state space where it's just at the edge of a phase transition, which is exactly where you want your neurons to be. You want your neurons to be exactly on the edge between synchrony and non-synchrony so that you can quickly get into synchrony and you can quickly get back out of it. Okay, so self-organizing criticality, another type of self-organization that seems to be rampant in the brain. Your brain seems to be tuned up such that the spontaneous synchrony is doing this self-organized criticality. So two types of self-organization kind of interacting. The avalanche events follow what's called a power law distribution. So a power law distribution is this thing where there's lots and lots of very small events. So this is like a tiny little avalanche, and then relatively fewer larger ones. Power law distributions show up all over the place in nature. Forest fires follow this, earthquakes, real avalanches. So there can be lots of little events and relatively fewer ones. And neural synchronizations are like this as well. There's going to be lots and lots of little neural synchronizations and relatively fewer larger ones, but there are going to be a few. Just by way of warning, these power law distributions show up all over the place. So it's not necessarily a result of self-organizing criticality, but it can be a sign of it. So this is like a normal distribution. Like these distributions show up quite regularly across different phenomena that aren't plausibly self-organized criticality. Number of lifetime sexual partners also follows this curve. So most people have just a few, and then a few people have like a ridiculous number. But I don't understand. There's no way of parsing that in terms of phase transitions and self-organized criticality, right? It's just a different mechanism generating the same basic curve. But in the brain, we have a pretty good story about how self-organized criticality would generate this curve. So there's a reasonable connection between the two. Yeah? Okay, so a kind of marker in some sense that the brain is self-organizing in terms of neural synchrony. So one type of self-organization organizing another type of self-organization in some sense. In philosophy, we talk about this kind of formal explanations in terms of emergence. So a property is emergent just in case the best explanation of it takes place at the level of the whole rather than the parts. This is another type of, this is the classic case of emergence of birds flocking. Extremely simple rules govern how the birds move. They're just trying to keep a certain distance between themselves and their neighbors and move in the same direction. So extremely simple rules result in incredibly elaborate and seemingly very organized overall organization. And the best explanation for this is not in terms of the rules, because the rules are simple. The best explanation is typically at the level of the whole. And I think I hope I've shown you a bunch of examples of this throughout the lecture. Yeah. So we're talking about a whole bunch of phenomena, the self-organized phenomena, for which the best explanation seems to be in terms of the structure or organization of the parts. And in some sense, that's going to be true anytime you have a multiply realizable system, isn't it? So if your system is multiply realizable, then thinking about it in terms of its parts is probably a dead end. Because the parts are not, if the system, as you've understood it, is multiply realizable, the parts are not what's explaining it. Because it could have had totally different parts and still been that system. Yeah? Okay, so this is just the philosopher's way of doing this. Briefly, I want to do the other thing that Horero said we needed to bring back from good old Aristotle, which is final causes. Final causes, final explanations. When she talks about adaptive complex systems, the adaptive part is invoking purposeful action. So these things seem goal-oriented. They seem to be moving towards a goal. This is more controversial than the formal causation stuff. But as it happens, my PhD advisor, Dennis Walsh, defends this idea. He's at the philosophy department at U of T. He's a very nice man. And if you get a chance, you should take philosophy of biology with him, because he's great. So he's also one of the only people who defends teleological explanation in the sciences. And he does it based on the best current understanding of causation. So he says this counts as a real cause, a real explanation. Premises are basically, any explanation contains the following two things: an invariance relation, something that stays the same across change, and some description that helps you understand why that thing stays the same across change. So in mechanistic explanations, the mechanism reliably produces a range of effects. Right? So that's the thing, the same mechanism stays the same, will generate a bunch of different effects. In teleological explanations, he says, the effect is reliably brought about by a variety of explanations. He thinks that only living things are like this, but that if you don't understand this property, you won't understand living things. So living things, all living things, have a huge variety. And the more we understand about biology, the clearer it is. We've got a huge variety of different ways of regulating ourselves. So you regulate your internal temperature, your blood glucose, all of the properties of you are intensely regulated by a whole bunch of different systems with the same goal, right? They're all trying to keep you alive and flourishing. Those are a huge variety of regulatory mechanisms. Now, sometimes one mechanism will get knocked out or can't work or is working too much. Other mechanisms will step in to compensate for the difference. So the activity of any given mechanism is not regular. The activity of any mechanism is very hard to predict, actually. What's easy to predict is the goal state, that the organism will tend towards the goal state. And our behavior is, of course, like this too. Everybody agrees that we are goal-directed. So my goal today was to get to this classroom. And if the bus hadn't been working, I would have walked. If the subway had been out, I would have taken a lift. You know, like I would have used many different means to get to the same end. And that seems to be what many living that seems to be a very broad characteristic of living organisms. So Dennis says we should allow teleological explanations back into our scientific worldview. Because if you don't understand how living things are goal-directed, then you don't understand their organization as wholes. So that's another possible Aristotelian notion that could be brought back. Okay, but let's leave that there. Again, this is much more controversial than the formal explanation stuff. I don't think Dennis is the only guy, but he's among the only guys. So again, controversy, big controversy. These are ideas under construction. This is all in alpha testing. Don't take this to the bank. But these are possibilities. really briefly before we're done, I feel an unrest, and we've already gone way past where we usually go. I just want to mention this predictive processing paradigm that is alliteratively making its way into contemporary cognitive science. Like, this is kind of the hot thing in cognitive science right now. And these are people who explicitly describe themselves as invoking self-organization to understand how the mind works. It's a quite fascinating perspective. And it goes like this. Almost everything that you experience all the time is a guess that your brain makes, rather than the world imposing it. So the standard way of thinking about sensory experience is that it's just the world imposing itself on you. The predictive processing account says basically most of the content of your experience is guesses that your brain's making from a kind of top-down prediction. And all your sensory experience does is provide an error signal. So when I walk into my apartment, when I get home, everything is kind of where it should be, because I don't have kids, I guess. Everything is basically where I expect it to be. So in some sense, it doesn't jump out at me, right? In some sense, you don't see the stuff. Now, if you focus, if you're like, I'm gonna really look at my couch, really take it in, you can do that. That's a thing that you can tune your mind to, like, not just to rely on the predictions. But if you're not doing that, you don't see the couch, do you? It's just not an error. You're just like, yep, everything there is where it's supposed to be. No problem there. So their thesis is that your mind is basically a prediction engine. So it's making predictions all the time at a bunch of different levels. Predictions at the very large scale, predictions at the very small scale. So I predict that if I turn my head, I'm going to see that wall, right? Prediction confirmed, hooray. So I don't get an error signal. And the fact that I don't get an error signal means that my brain doesn't have to deal with a whole bunch of information. It doesn't have to reprocess all the information from just confirmed predictions. So this is a cycle of reciprocal prediction and prediction tuning up. So you're tuning up your predictions via the error signal given by perception. Thomas Metzinger described this as the idea that perception is basically vividly hallucinating at the world. That your perception is basically a constantly controlled hallucination. It's a hallucination that is moderated by sensory input to keep it roughly on track, but that almost your entire sensory experience is generated from within. And it's only when something unexpected happens that the world imposes itself on your vivid hallucination. And that there's sort of layers of predictive modeling that are self-organizing to minimize the error signal. And that's what perception is. So this is kind of the cutting edge of third generation COG-sci. This is where cognitive science is going at the moment. It's the kind of the hot thing that's happening. And it's explicitly a system of self-organized constraints, sort of like being imposed on perception, and perception imposing constraints on your models, and a reciprocal causal relationship between the two. So there's an example of third generation COG-sci, which actually uses this abstract stuff that we've been dealing with. Okay, so that's it for AI. That's it for the kind of AI chunk of the course. On Thursday, we're going to start in on philosophy of mind. I've been hearing a lot of you saying, where's all the philosophy in this course? So now we'll start doing some philosophy. We'll talk about the simulation problem. Okay, thanks everyone.